Okay, so let's get some of these applications in, and then we can talk about homework questions you might have. I will point out again that all of the lectures, the whiteboard stuff, just downloaded, converted them to PDF, so you can go in there and view those if you missed something. I'll just click on it here. I don't know why they don't name these better, but the YouTube channel that has all this stuff on it. It has this class and Calc 3 on there, so you might have to sift through a little bit, but it's got all these recordings. You know, if you want to zoom through that or play it back at 5 times speed or whatever, or just zoom through to find the place that you're interested in. So, okay, so using this stuff, specific applications is displacement. So just like we had before, you can use this to find displacement. I'll be more precise in a second. You can do what's called area between curves. You can do, and you can also do what's called the average value of a function. All of these things can be gotten from a definite integral. So for displacement in particular, the displacement is, well, all you do is you just take the definite integral from your whatever your first time is up to your second time of the velocity, and that's it. That gives you displacement. So all you need to do is find the antiderivative of v, plug in the 2 bounds and subtract, boom. You now have displacement, which again does not mean distance traveled. It means how far away are you from the starting point. So just like we talked about earlier, you can go from the starting point somewhere and come back to the starting point. Your displacement would be 0 because it's always just from the start point to where you end, not how far you travel to get there. Area between curves is if you were to draw 2 curves, and I don't know what they look like, but we'll do some examples, that if I draw one curve, which is like f of x, and I drew another curve, which is g of x, y equals g of x, and I wanted to know what the area between these 2 things are, then it's, you know, the sort of same idea. You want the area in between them, then you basically find the area for f, and then you find the area for g, and then you subtract. I think that probably should make sense. But if you condense this down, you can get to a to b of f of x minus g of x. You can combine them using these rules for definite integrals, where you just subtract the functions and then do your fundamental theorem on that. And then the final one for average value, and don't worry, I'll do some examples, but I'm just trying to get the sort of formulas in here. That for average value, let me minimize my picture here. Then if you have your function here, your function is going to start at some value, here at a, it's going to do some stuff, it's going to go up and down, and it's going to stop there. So here's y equals f of x. So it starts at some point, it ends at some point, but like what's the average that you were in there? The average value of the function. If it was a straight line, you would just take the last value and the first value, and you would just take the average. So you add them and divide by 2. Problem is if you start going up and down, it's a little hard to see exactly like where's the average value? Does that even make sense? And the crazy thing is it turns out that the average value is related to the area underneath, where you just take the area from a to b of your function and then divide by the width of the function, which is the distance from b to a. So that's b.
So can you repeat exactly what the average value is again? I didn't exactly hear you.
Well, yeah, so let's see. A function, well, I'll do it. Let me do an example of it on that one. But the point is if you just went from here to here in a straight line, just straight line, then you're ending at this high point, you're starting at this low point. The average is going to be right in the middle. And so you just go right in the middle and you say, boom, that's my average think of this as a height, maybe. My average height is here. The problem with this one is like I go up and I come back down, I go down, I come back up. The question is like, what average height was I at over that sort of, this you know, you're walking up the side of a mountain or something like that. So sometimes you were going up, sometimes you were going down. Maybe you even went all the way up and then came all the way back down. Is there a notion of like, what was my average height for this entire trip? And the answer is, it turns out that it's exactly this area. It's the same thing as saying, well, if I knew the area underneath, what value could I plug in? I think I can even change colors here. Maybe I can, but I haven't figured that. Look at that. What rectangle could I put in here so that the area under the rectangle is exactly the same as the dark area under the black curve? And whatever that value is there, that's called the average value of my function. So you can think about it as like the average height over all of the entire path, or you can think about it as the height that would give me the same area for the rectangle as it did for the complicated curve on the end. So let me convert back. Let me do some examples of each of these, and then maybe that'll make sense when we actually get some numbers in there. Maybe the area in between two curves. So let me get one that's kind of nice that you see here. So we'll say, for example, find the area between y equals 3x minus 2 and x squared plus x minus 5. Okay, so I'm a big proponent of pictures, so we'll draw a picture here. So draw each of those two graphs. So x, y. The first one here, y equals 3x minus 2, is a line. So if I was to draw that line, all I need to do is figure out 2 points on here. So if I stick in x equals 0, I'll get -2 at that point. If I stick in, say, 1, I'll get 3 minus 2, which is 1. So I know that my picture is a line. Challenged here. Oh, that's terrible, but that's what it is. Sorry. Okay, so there's that. That's the line. The other one is actually a parabola. So we'll probably need to plot a few points on that one. If x is 0, then y is minus 5. So that was minus 2, 3, 4, minus 5. If I plug in 1, I'll get 1 plus 1 minus 5, so that's -3. So 1, 1, 2, 3. I don't necessarily know that this is the bottom of the parabola, so I'm going to plot a few more points. If I stick in 2, I get 2 squared, which is 4, plus 2, that's 6, minus 5, I get 1, which is, let's see, 2, 1, right there. And hopefully this is going to work. If I plug in 3, I'll get 9 plus 3, which is 12, minus 5, which is 7. And actually, if I plug in 3 over here, I get 3 times 3, which is 9, minus 2, which is also 7. So up here somewhere, I have my parabola, which continues throughout, but it hits my line there. It's going to come down, and at least it comes down to here. So let's see what happens on the other side, say at -1. So -1, I get, let's see, -1 squared, that becomes 1, plus a -1, so those cancel out, 1 and -1, so I get -5. And if I plug -1 in here, then I get -3 minus 2. I also get -5. So at -1, this thing hits at -5 there. So it actually turns out that the parabola comes a little bit lower and then turns back up. So that is terribly ugly. You can at least see, hopefully, if you drew the line and you drew the parabola, that there is an area that is captured in between. And that is the area that I'm talking about. So this takes some time to draw these pictures. But if you do, we can just go back for a second. We can see that the area between the curves is given by this formula, where I take the curve that's like the top one, and I subtract the bottom one off, and then I do this definite integral. So we can try that here. So that means that the area will be the definite integral from, and I know now that this, they hit at -1 and 3. So the area is going to occur when x is between -1 and 3. The top curve, the f, the one that's on the top, is the line. It forms the top of my curve, or top of my area. So that'll be 3x minus 2. And the bottom curve, the one that's below, is the other one. That's the bracket. X squared plus x minus 5. Okay, so all I need to do is figure out a function whose derivative is this inside. And then I can use the fundamental theorem by just plugging in the values. But maybe I want to clean it up just a little bit. See, I have an x, I've got another x, and I've got numbers. I think I could probably combine this into one nice thing. So let's look. If I combine the x's here, that's 3x. And if I distribute the minus properly, this would be minus x. So I have 2. Yeah, so 3x and minus x here. How about the numbers? I've got -2 and then minus distributed on -5. So -2 and 5, that'll be 3. And then the x squared is left, and it has a -1. So that's a little bit nicer. Now, if I can try to get this all on one slide, I'm going to need to find a capital F so that if I took the derivative of it, I would get this. So what do I take the derivative of to get 2x? The answer is x squared. What do I take the derivative of to get 3? That's 3x. And what do I take the derivative of to get -x squared? That would be -x cubed divided by 3, or -1/3 x cubed. And again, plus c, but I can take any answer I want, so I'm going to leave the c off. So that's my antiderivative, my indefinite integral. So based on the fundamental theorem, is I just need to find what capital F at 3 is minus capital F at 1. And that will take care of that. So plug in 3 into this equation. I'll get 3 squared, I'll get 3 times 3, and I'll get 3 cubed divided by 3, and then plus and minus. So 3 squared is 9, 3 times 3 is 9, so that's 18. X cubed, 3 cubed is 27, but then I divide by 3, I get 9. So it'll be like 9 plus 9, but minus 9. And so the answer is 9. What happens when I plug in 1? If I plug in 1, this will be 1, this will be 3, and this will be a third, and then that part's subtracted off. So it'll be 4 minus a third. So let's see, 4 minus a third. 4 is 12 thirds, so I take away 1/3, I get minus 11 thirds. And so I'll have 9, and I got to subtract 11 thirds. And you can do that in your calculator, I guess, or we can say, you know, how many thirds this is. 9 is 27 thirds. Take away 11 thirds. So 27, take away 11, we get 16. And so we get that the area between, again, just to emphasize that this is the area between the curves, is 16 thirds. And I probably could have done a square or some triangles or something like that to guess in advance what the answer is. We just sort of jumped over that. And at least we drew it, and we have that that's the estimate there. So it's kind of a lot going on there. You do have to draw the graphs. You do have to figure out which function is the top curve, which one is the bottom curve, and so forth. Maybe I should just do one more because I know that we're kind of fading out here a little bit. But let's grab one over here. For example, suppose that the function is given by, well, we'll just do it like this. Suppose the velocity is t minus 1 squared on the range from 0 to 3. So t is going from 0 to 3. So now instead of having x's, we're back to t's. Then the first question will be, what's the displacement? And the second question is, what is the average velocity on that range? So what's the displacement and what's the average velocity? So we could do a plot of this. Maybe I'm just going to skip it for right now. I'm already breaking my own rules, but so we have enough time to do other stuff. So displacement is just the antiderivative, or the definite integral, so it's a number from 0 to 3 of t minus 1 squared dt. Just straight up, it's that. So now I got to figure out what is the antiderivative of that guy right there. So there's two ways to do it. One is to come down here, and my capital F will be antiderivative of t minus 1 squared, which is, maybe if you want to multiply it out, you can. T squared minus 2t plus 1. Make sure when you square this out, you do it properly, with distributive property. And now I can do each one. So that's t cubed over 3, or 1/3 t cubed. In the integral here is t squared and t. So all I need to do is evaluate that capital F at 3, and I can evaluate that at 0 and subtract. So if I stick in 3, I'll get 27 over 3, which is 9. This will be 9. This will be 3. So 9 minus 9 plus 3 will be 3. If I stick in 0, well, that's pretty nice. 0, 0, 0, subtract 0. And I get that the displacement is 3. If this is measured in feet, for example, this would be measured directly that, 3 feet. So I'd be 3 feet away from whatever the starting point is. And then the nice thing about this is that the average velocity formula is the exact same thing, 0 to 3, except I divide by 1 over the difference between the start point and the end point. And so this will tell me over this range, sometimes I'm going fast, sometimes I'm going slow, but if you could average all of those velocities out, this is 1/3 in front. This definite integral I just did, so that's 3, and I'll get 1. Now, if you wanted to be careful on the units, this is 3 feet. These are measured in seconds, 0 to 3, so that would be 1 foot per second. So you can get the units out of it. You can see at the beginning, if we were actually to stick in 0 and square this out, I would get 1. So it's going 1 foot per second. But then at the end, if I stick in 3, I would be going 8. Or sorry, 3 minus 1, which is 2 squared, I'd be going 4. So at the beginning, I'm going 1 foot per second, and then at the end, I'm going 4 feet per second. You're like, wait a second, how did you get a 1 foot per second average? Well, if you plug in t equals 1, this would be 0. So I'm actually slowing down from 1 to 0 and speeding back up to 4. And my average over that entire span is actually just 1 foot per second. So that kind of knocks out displacement, average velocity, and the previous one was the area between the curves. So at least that gives you some examples of each of those, and I think that's probably a decent place to stop for 5.4. So I'm actually going to just do that. Real quick, stop recording on that.